Yes. So I'm going to talk about perception for autonomous breathing robots, and those robots will be operating in grasslands. We have seen quite a few works already where robots operate in crops or other settings where plants are nicely aligned in rows, and this is a little bit more chaotic what we have here, right? And of course, for those of you who saw the poster outside or the short introduction we have here, this is the visual wind detection part of that system in that European project that I was talking about. If you haven't watched that, you are not missing much. I mean, we're going to talk about perception here. So, why weeding, robotic weeding in grasslands is important? And the motivation is sustainability. So I guess we're all a little bit familiar with these 17 colorful little squares here. We're trying to make the world a more sustainable place, and why is that? I was born in a planet that was populated by 5 billion people. Right now we're 7 or 8, and we are doomed to be even more in the future to come. So apparently we need to produce more food than ever today. And what is more important is like tomorrow we will need to produce even more than what we need today. So sustainability becomes a key issue here. So how can we be more sustainable? Robots is a way to go there, not the only one, but one way of going there. And obviously perception is a key element for those robots to be autonomous, because if you have a robot that you just operate, I mean, you don't gain much. It has to be autonomous. Perception is key. And autonomous robots, they do exist out there to some degree, to some or lesser degree. And one can actually observe that those autonomous robots, they are deployed in structured environments or semi-structured environments. However, agricultural environments are, in many cases, not structured or even semi-structured, they're completely unstructured. They could be also semi-structured, but I mean, in many cases, they are completely unstructured. And of course, in agricultural robotics, you are supposed to work under any weather conditions, right? So you are out below the open air, and yeah, changes in lighting or weather can actually happen at any time. And agricultural environment can often be like one of a kind, right? I mean, there's not a second place on earth that looks like this one. And it's a completely non-standardized place in many cases. So the question arises, how can agricultural robots operate autonomously in such a mess? Perception is the key to that. And for perception to work in such a messy environment, it needs to be robust. Pretty much every situation that an autonomous system will be exposed to, it's going to be a unique one. And it has to be adaptable, right? So things change over time. Summer gives way to autumn, and so goes on. So things completely change, and our robots need to be able to adapt to that. Finally, our animals are not so afraid of robots, apparently. So this is from a previous project that we had. I mean, the video is breaking here, but you can see a cow that is actually very interested in our little robot that we have deployed at the time. She actually invites her friends to come over and join her in licking our robot. so yeah, so it's a nice task to do. I would argue that there are two main strands of robotics research when it comes to agriculture. And let me, like, on one side, put those large machines. So those are the standard classical agricultural machinery that started like as manually operated, but then they have been more and more robotized, right? Becoming more and more aware of the environment, and maybe autonomous by today. And there are also those toys that we have in our university labs that we start to mature little by little, so they can actually be mature enough to make it by themselves out in the wild. And I mean, at the Technical University of Denmark, where I come from, we're actually working in both categories. So we're collaborating with ACO, which is the brand name behind, or the mother name behind brands like Massey Ferguson's or Fence. And we have also our own little toys that we're trying to do, make them mature enough to make that outside. In this talk, I will be talking about the little toys that are trying to find their ways in the reality. Let me focus on a specific type. So I already promised that I've been talking about grasslands. Let's talk about dairy farming in open grasslands, and especially organic one. So apparently, the area that is devoted to organic farming is growing. And this all happens both in the small countries of Europe, like Netherlands and Denmark, but you can also see it in the big giants of Europe. Talking about giants of Europe, in the States is probably an exaggeration, but the big countries of Europe, they also have the same tendency. So more and more interest is shown on organic dairy farming. And when it comes to dairy farming, one of the reasons that can make farming organic or not is actually how we deal with weeds. And in this work, I will be focusing on a specific type of weed that is very widespread all over the world, and it's a Rumex obtusifolius, or broadleaf dock, or there are many names around the world for it, but I will be referring to it as Rumex for now. And the typical way of dealing with this annoying plant is by just spraying MCPA on it. So some chemicals, but those chemicals are apparently bad for everything around. They're bad also for the weed, but we don't care about it. But they are bad for everything around it. Like we can actually find it in our water resources. So apart from just massively blinded spraying or selectively spraying, which is still spraying, we have other means of controlling this type of weed. That can be laser, that can be steam, flame, I mean, all sort of medieval tortures that you can actually imagine. And there are simpler things like mechanically removing it, or just bring your goats, let's say, on the thing, and then they will eat it. What we don't want to do is we don't want the cows to eat it. Because if this weed becomes too widespread, it actually takes a place of normal plants. And if the cows eat too much of Rumex, I mean, there are some acids in the thing, so the milk quality drops, and I mean, if seriously consumed, I mean, it might be bad for the health of the animal as well, right? While the goats are much more resistant, but we're focusing on dairy, right? So, talking organic, there are some methods that are better than others, and yeah, we are gonna see how a robot that is equipped with vision can actually identify these types of weeds and use some organic friendly ways of controlling it. So, weeding in grasslands, what is our starting point? Already in this room, I mean, from the relevant literature, we know like that we have been doing weeding for a while. And Chris McCool, some minutes ago, he was talking about weeding himself. And this photo is coming from your group, guys, and you have been doing some incredible work trying to find out what is the good crop versus what is the bad weed. And the simplification here is it is a structured or semi-structured environment, right? So you have nice rows of crops, pretty much everything in between should be a weed, and then you have like a specific type of a good crop that you want to keep, and pretty much everything else could be, generally speaking, removed. So this is the starting point here, but I mean, our use case is a nightmare compared to that, right? So we have like an endless, and this is a relatively nice environment. It's a very flat environment, right? I mean, come visit me in my hometown in Greece, and if you want to find such nice flat environments, maybe that's the case in Netherlands or Denmark, but so our scenario deals with Rumex in grassland. So it's a green target on top of green background, arbitrarily placed everywhere, right? So there's no structure there. So it's a computer vision nightmare on how to identify it. So this is where that European project comes in the game, and we are trying to use Galileo localization. Galileo is pretty much, an oversimplification, is the European equivalent to GPS, to approach the goal of zero herbicides in daily production. And how do we do that? By trying to control the rumex weed in a herbicide-free manner. And this project is comprising of different modules that will be integrated in the central robot that is here. Of course, the Galileo satellite flies over us, telling us where we are. So we have EGNSS, the European, the European GNSS system. So we have an antenna there, we have a receiver, and we are using the high accuracy service that the Galileo provides for commercial purposes, in contrast to GPS. And we are doing the weed detection, which will be the goal of this, the focus of this talk, to control either by laser or electric weeding this rumex plant. And of course, there needs to be like an entity that kind of takes over the mission control and navigates the robot. But let's focus on the weed detection. So this is where we start with the Husky robot. So we mounted cameras, and we wanted to mount also some laser control units there, but it very quickly made clear that that's not big enough to carry all the units, all the power. So we actually switched, and this is the latest development here. So we took another bigger robot that we will be using to deploy. But this is currently in integration phase. So this is still a work in progress over there. So we want to detect weeds in grasslands, and like every other lab on planet Earth, we will be using deep learning because this is what people are doing nowadays. So deep learning can actually provide some elegant solutions in finding those complicated targets on this complicated environment. However, they have the known disadvantage that they require huge amounts of training data to actually perform. So that's what we did. That's what we did. We went out and we gathered data. So we visited 3 different farms in the larger suburb area of Copenhagen, in the island of Sjælland. We have been visiting during different days, and we have not only capturing. So we have been there with our Husky. So it was not only images that we captured; it was actually sequence of images, together with their GNSS coordinates, together with IMU data, together with odometry. So we have gathered in total far more than 5,000 of those unique points, image, GNSS, IMU, and we started processing them manually by drawing more than 15,000 of those bounding boxes out in the wild. And we also experimented a little bit with some of those images to do like pixel-wise annotation for possible semantics annotation tasks. Yeah, so we have actually packaged all those things neatly, and we're actually working on making this a public submission that will introduce these data sets to the public. So we believe, the problem that we were facing, not being able to find proper data sets to train, we could actually help the community by just making this data set available. So more to come, I guess, when the paper gets accepted. Fingers crossed. Yeah, but while doing it, something interesting occurred to us. So, for example, when visiting a certain field on a certain day in search for a specific species, that rumex thing, it occurred to us that the different plants, they have relatively little variance from one another, right? So it's the same day, same this, right? So many plants were in similar growing state. They have been experiencing the same weather pretty much. They are like relatively small geographic areas. They were not completely different from one another. So then the question that arose, or like the possibility that arose, was like, could it be that we don't actually need to have so many plants or so many leaves of the plant to train a segmentation model? Can we actually use only a handful of those leaves, a handful of those plans to artificially train those while still being able to describe the vast majority of the available leaves, of the available plants on that specific field, on that specific day, right? And that brings me to our next research work, which we call it few leaf learning, and that was published in previous IROS. It was finalist for paper on agro robotics, just a finalist. So what we did is from a single visit, we found and manually segmented some leaves, right? So we had such a number of leaves that we had segmented. And the way to segment those leaves is like this, right? It looks like that. So many of us might have been this like notoriously boring and not very fulfilling operation, like manually drawing the threshold around, right? Yeah, and it looks as boring as it is. So the idea was like, okay, now if we did it for only a handful of those leaves, we could actually use those handful to artificially generate more. So what we did is we took some leaves and we also took a number of clean, weed-free images from the same field, right? And then we wrote a simple script and we took those leaves and then stressed them a little bit, but in a mostly circular manner, because this plant actually has some circular structure. So we started superimposing those leaves on those clean backgrounds, right? So we artificially started creating data. And of course, yeah, you would stress them a little bit. You would apply any sort of transformations that you would like in order to produce unique images as you go on. So we have this synthetic image composition engine in our hands, very simplistic. We even tried like, okay, how do you blend the thing? Do you need to add some kind of like blurriness in the end of the leaves when you superimpose it? The answer is no, it doesn't make a huge difference, right? I mean, yeah, you can add, but I mean, in the end of the day, you can just copy paste those leaves on the images. So we use those synthetically generated images to just train standard Pokemon, right? So we just use a PSP net and we trained it on those images. And once trained, we started treating the real images, right? So, and I mean, it's already now impressively similar how synthetic images and real images look alike. So we run prediction on those real images, and the result looked something like this. It's not perfect, but it's great, because in the end of the day, we don't want the perfect segmentation of every single leaf, right? We just want a cluster that signifies that there's a plant here, go there with your laser, and then like Star Wars like go and just cut it. So that was actually pretty interesting to see. And of course, the thing that we did is, or the million-dollar question is, how many leaves is few leaf learning, right? So how many leaves do we need? In that specific day, in that specific field, for that specific species, we were actually trying to run the same experiment for a different number of leaves. And what we found is like approximately at 9 leaves, we got to the level of performance that kind of like stabilized till the end of the experiment. So we wouldn't see huge improvements if we used 20 leaves or more. So 9 leaves, different combinations would actually give us this. So this not so fancy engine is available on GitHub here. And you can actually try it for yourself. And it's remarkable how well it works. And I listened to Chris McCool for like like half an hour ago, and he was talking about simplicity. And yeah, that's along this way. I'm a huge fan of simplicity as well. So now we were able to have those not perfect but existing masks out of my neural net, and then we would be able to just go manually if we need it and start like fixing the thing, right? And that just fixing the proposed masks is just a fraction of the time compared to this to that old school boring process, right? So I think on average, it's not a systematic measurement, but on average, we found out like we needed like a quarter of the time for the same image, because now we have a starting point. you can actually focus where you need to start and only fix manually those remaining parts. So again, the problem is we need a lot of training data. That was one way of somehow artificially creating those data, and I mean, maybe using them as a starting point for doing a better work.
Those are all the people.
Then we started looking into self-supervised learning, because our friends in computer vision, pure computer vision, they talk about self-supervised learning as being able to reduce the for the label data. So we took the recent work by scientists in Facebook research at the time. Now it's Meta AI or whatever they're called, and there is this SWOF paper down here presented at Europe's 2 years ago.
Hey, this is it. There's nothing to see.
The idea is that the typical pipeline is that we take a pre-trained network. That's what we typically do, right? And I mean, this network is usually trained on a big data set like ImageNet. And then we have a number of relevant labeled images, relevant images for our task that we label themselves. And then we fine-tune this pre-trained network on our images and then deploy it. So what we thought is like, instead of taking a pre-trained network, let's take a completely empty network and start training it from scratch, from the pre-training. And using SWOF, you don't need labeled images. You just need to find images and start feeding it with. So what we did is just we scrap the web for images that fall under the category grasslands or agriculture. So we start feeding this model with a lot of relevant but unlabeled images from the web. And funny enough, this self-supervision can actually train a model that is good at creating meaningful features for agricultural tasks, right? And a pre-trained model on ImageNet, it has been trained on bananas, monkeys, and all sorts of stuff that are not necessarily interesting to us. But here we had something that has only seen agricultural related stuff or grassland related stuff during training. Yeah, so this SWOF is based on contrastive learning, which is a very beautiful concept, if you ask me. You can look up, or we can have a discussion later on with how that works. But once we feed it and then once we feed it and let it be self-supervised with those unlabeled data, we have now a good backbone, and then we can actually fine-tune it again with a handful of images. And those images we still need to label ourselves to kind of avoid it. So now we took this thing and we compared again the standard like ImageNet pre-trained deep neural network. And this is the blue line, and so you see how it performs. Like at 100% on the x-axis, you can see the full data set that we have manually annotated. So being like fine-tuned on all the images that we have available, and progressively, as we go down to one shot, removing images for fine-tuning. And this is how the pre-trained on ImageNet network has been performing on blue. And the other two colors, it's our like self-supervised model. So one can argue like for the full data set that we had in our hands, for 100%, all three models are performing about the same, right? I mean, small differences there. However, as we fine-tune the net with the fewer and fewer images, we see that the ImageNet pre-trained network starts falling drastically, while we're still keeping up. We are downgrading our performance, of course, but we're still doing quite well. So that actually shows that you can actually use fewer labeled images to fine-tune your model. And most importantly, you are not anymore required to go with what's available out there trained on ImageNet. You cannot train on humans them yourself, right? So you need to find the model pre-trained already. And there's like a number of pre-trained models that are there. So if you wanted to make some change in this deep net architecture, you're not allowed to do that because then you don't have the pre-training weights anymore. However, here you can do whatever you want. You can do whatever change in the network you want to do and still be able to perform better than the vanilla ImageNet thing because you can actually use self-supervision. And self-supervision is quite cheap to obtain here. So we have published this work recently in Computers and Electronics in Agriculture, and it seems like it works pretty well. So I would like to start wrapping up here. I would like to emphasize that perception is a key element. However, in order to have robust perception, we need normally to put a lot of manual effort. And this manual effort is sometimes not very convenient. So the idea is how to make the perception more robust without putting too much of a load. And this line of research that I have been presenting here is actually trying to follow up on this, on how to make clever decisions, simple decisions, in order to get to free us up a little bit. So hopefully we will have robots sharing the grasslands with cows very soon. And at this point, wrapping up my talk, I would like to thank my PhD student, Ronya, who's on maternity leave. Otherwise, she would have been here with me, giving the talk with me. A lot of, or most of this work has been her effort. Yeah. And with this, I would like to close.